Let me ask what you see on this slide and how you interpret it. May I ask Lina?
Yes. So I see light wave, which is the electric field perpendicular to the magnetic field, which is and this is the equation that expresses the electric field.
Okay. Does everyone agrees with it? Are there any additional comments? Or please show if it is sufficient or if I need to give more comments. Yeah, thank you. Kia, are you okay with this explanation or more is needed? Oh, okay. I think you decided to type more comments. Okay, Boston, would you like to give more comments?
Well, it just looks like you are depicting an electromagnetic wave, giving explicitly just the electric part of the field, not the magnetic part. In that wave, you're expressing it as a complex wave rather than as like a sinusoid. Well, it is a sinusoid, but complex one. Where k is the wave vector, omega is the frequency, and then you have the phi as the phase shift with the amplitude given by epsilon naught.
Okay. So I believe so. If there are more questions, Stephen, are you fine with it, or more explanation is needed?
I'm fine with it.
Okay. So, Kia, if you need more, these arrows are strengths of electric field that moves charges and magnetic field that rotates the arrow of compass. And if there is a source of electromagnetic radiation, these fields in a certain point of space are oscillating. Or if one looks through the range of space, then they're also oscillating. So in time and space. Okay.
So from that, we are what we are looking for.
So we are yes, we are looking to explore a molecule, right? That is being irradiated by light. The intuitive expectations are that the oscillations, light, electromagnetic radiation, light, so one can photoexcite molecule and promote electron between states on one hand. On another, if these oscillations of electric field are very slow, then it may induce polarization of a molecule if those are in like microwave, or so there are some changes to like positions of ions and electronic clouds, because in the molecule electrons are attracted by ions, right?
Yeah.
But if we add external electric field, electrons want to please this field. Wherever a field directs, electrons will move or respond to electric field. And I'm not going to convert our class into physics class, but response of materials to external electromagnetic irradiation is an integral part of any material science. We cannot live without it. Make sense?
Yeah, it's okay.
Yep. Now, let me ask Stephen, how do you interpret this slide, especially the stuff in this circle. I apologize for ugly drawing, but any comments or any? Of course, you can say it is some unreadable garbage, but anything behind that?
It appears to be measuring or depicting the electric dipole moment of a specific molecule in relation to time.
Okay, good. Thank you. So most of molecules are neutral. So amount of positive and negative charges, electrons and ionic charges are compensated. So if there would be ions in electrolyte, then electric field makes them to move, right? But if the molecules are neutral, then electric field will not move them. They will stay wherever they are. But if the molecule is polar, if it has dipole moment, electric field will make to reorient. Okay, and please stop me anytime if more comments are needed. So electric field reorients molecule and makes it to rotate until the line which connects positive and negative, which is also called dipole, until this line will be oriented with the direction of electric field. If this angle between these two lines is non-zero, then the system of electric field and molecule will be unstable. So it will be some increment in energy. As soon as this arrows will be parallel, the energy will be minimal. Okay, would you interpret it? Would you tell how you interpret this last statement?
Which one, Professor?
The idea about alignment between dipole and electric field.
Sorry, Professor. This time I'm not able to say anything because I don't have enough knowledge about this.
But just what you how you interpret it, not the knowledge, but impression, what you hear and interpretation. So what is dipole? Would you please try?
Professor, I think it's better if you explain.
So dipole is the line that connects positive charge with negative charge. Okay.
Yeah.
And the dipole is equal to the length of this arrow times the amount of the charge. So if you have positions of positive and negative, R plus, R minus, then the dipole will be equal R plus minus R minus time, and we assume that they have the same charge times the charge of this particles or average charge of the molecule.
So dipole is like a bond between two charges.
It's not wrong. Typically, one speaks different languages, but yes, bond between two charges or lengths of bond between two charges.
Okay. Yeah, when you draw, then I think that this one will be dipole.
Now, which? Let me ask you the following. So suppose we have electric field oriented upwards and then the dipole oriented at 90 degrees. Here D, here E. So it is situation number 1, and here is situation number 2. Electric field is again in the same direction, and dipole is going in the same direction. So which situation is energetically more favorable? So this is question for K. Where the energy will be bigger, where the energy will be smaller.
The second one is bigger.
First one is bigger. I don't.
First one is bigger. Second one is smaller.
Yes.
So here is convention. Energetically favorable means smaller energy. So dipole wants to orient along the field. And same when you become a tourist and walk in the forest with a compass, the arrow of compass follows the magnetic field, right? Arrow of dipole follows the electric field, which means we can call this parallel, and this we can call perpendicular. So energy of perpendicular will be bigger than energy of parallel. Okay?
Yeah.
Good. Now, I'm going to say something relatively simple, but if you were not analyzing this aspect of material world, just be aware. It will be simple but new. So let's convert this little exercise into purely mathematical form. So suppose we do have total energy operator of a molecule, which we use like a Hamiltonian in molecular Schrödinger equation. We were assuming that the molecule is isolated. So it is a universe which has only one molecule and a vacuum around, right? The whole universe consists of only one, titanium dioxide molecule. And there are no stars, no planets, only one molecule. But now we consider a little bit more complicated universe where there is a homogeneous electric field. And the molecule has a dipole. So how would total energy, how would the Hamiltonian of the molecule change in presence of electric field? Sarah, would you like to try?
Excuse me, can you repeat the question again?
Yes. So suppose we know a Hamiltonian total energy operator of a molecule in a vacuum. Now, to this vacuum, we add strong electric field. And we also suppose that it is a polar molecule with non-zero dipole. How the total energy will change?
I think the total energy will increase, yeah, because we insert another electron to the system.
So electric field is not an electron. It is a field which is introduced at each point of space, right?
Oh,
and
okay.
The answer of the equation, which is also shown in this slide, but the answer just interprets this little thing that we just discussed. So the change of the total energy will depend on mutual orientation of the field and the dipole of a molecule. So if we rotate the molecule in space, for example, with Gauss field, the energy will change.
Yeah, that's true.
Okay.
Yeah. Yes.
So Sarah, you may just repeat the answer of K. In which situation energy will be bigger? When it is perpendicular or when it is parallel?
The first one. Perpendicular.
Has bigger energy, correct?
Yes.
Now, thank you. What if the angle is neither 90 nor 0 degree? If it has some like 45 or 30 or whatever, so some angle theta. So there is a way to say that the energy will be energy contribution. Let's say energy prime will be value of dipole times absolute value of electric field times cosine of this angle. And this equation, cosine of 0 will be 1, so it will be maximum. And it will not match our intuitive expectations. So we need to add minus sign. So minus cosine. So when they are parallel, energy is minimal. When it is 90 degrees, it increases, right? So this contribution is often written as scalar product of vectors. Vector mu dot product by vector e. And since we introduced the minus, we should put it, we should keep it. Make sense? Kay, would you share your impression, like how dot product of two vectors relate to polar molecule in electric field?
God.
It's just repetition of the same stuff we just discussed 5 minutes ago.
Yeah. Let me. If I'm wrong, then please, Professor, correct me because. Okay, so like if the angle is 90 degree, the dot product of the electric field will give you the maximum value.
Okay, I will correct later, but keep you're moving in the right direction. Keep going.
And actually, it's electric field totally depend on the angle between electric field and the dipole.
Correct. Energy depends on angle between electric
energy.
Yes, yep. Good enough. Thank you. So maximum value will be if the dipole will be directed against electric field. So if the dipole will be opposite direction, right? It will be bigger than 90 degrees. But if it is parallel, it is minimum. If it is 90 degrees, it is increase. And if it is opposite, it is maximum.
Yes.
Are you happy with the dot product notation?
Yeah.
Okay. Anyone wants to criticize dot product notation? No one. Okay. Now, please follow me on watching this little blue box. So Hamiltonian equals Hamiltonian without interaction minus product of dipole times electric field. So it is Hamiltonian of a molecule in presence of electric field. And this dot product is energy of interaction between light and matter. Make sense? Steven? Are you okay with it? Okay. Yeah. Let me quickly check that I have the right slides. I may have something a little bit better. Yes, I have the one with maybe edit. Different version. So here we see absolutely the same equation, just typed better. Hamiltonian, non-interacting minus electric field, which depends on position in space, times dipole. The dipole can be defined. So dipole is an operator, can be defined as summation of all positions of ions for positive contribution minus summation of all positions of electrons for negative contributions, right? And now there is a little discomfort in the following sense. When it is hard to intuitively think of it because we need to think not about one positive and one negative, but we have like several positive and several negative. And then the dipole will be arrow connecting average midpoint between all positive and midpoint between all negative. And number of positive and negative ions and electrons can be like hundreds, but the definition will work. Now, what I want to show, what is my goal? Suppose that I have some very oversimplified multi-electronic molecule, maybe something like H2, but I will not tell what it is. Just a molecule which has two orbitals filled with electrons. And I applied electromagnetic radiation of certain frequency to this molecule. And I want to observe that electromagnetic radiation will promote electron from occupied orbital E2. So we have two originally occupied to virtual orbital E3. Okay. And in order to practice this consideration, I will have the following players in this game. I will have multi-electronic wave function in form of Slater determinant. And I will have an operator which will be dipole that we just defined. And then the probability for this arrow, for this transition, that light promotes electron from occupied to unoccupied, should be proportional to the matrix element of this interaction. Please mute the microphone. I think someone is giving a little feedback. Thank you. And I will ask you to bring the microphones back for discussion. But so we are looking for matrix element of the Slater determinant corresponding to initial multi-electron determinant and final. And this initial and final determinants, initial and final multiple electron wave function will correspond to configuration. So initial is when we have, I will forget about spin and just draw electron as a little circle. So number 1 and number 2 are occupied with electrons, and number 3 is empty. So it is initial. And final, we will have number 1 occupied, number 2 empty, and number 3 occupied, because we promoted the electron from orbital 2 to orbital 3. Make sense? So we need to apply our knowledge, our machinery of equations that we developed for this situation. And do not worry, you did much more complicated considerations. This is not the highest challenge. Okay. So I'm going to use the following things. So for the initial determinant, or initial, I will use multi-electron wave function of 2 electrons, and they will be product of the first electron in orbital 1, second electron in orbital 2, right? So 1 and 2, and electron number 1 on first orbital, electron number 2 on second orbital. Although electrons are indistinguishable, and I need to cut this little image from our recordings, otherwise I will be fired. This is only little demonstration. Now, what would happen to multi-electron wave function upon we perform excitation? So electron number 1 will still be in the orbital number 1, and electron number 2 will be on electron number 3. So 1 in 1, electron number 2 in orbital 3. So this there are two products in the initial and final wave function, right? Okay. And here is our operator. So I'm going to practice this matrix element according to the following protocol. So in the matrix element, I will remove coordinates of ions because they are not getting changed if the electric field is changing quickly. So they will contribute only a constant to final answer, and it will be cancelled and removed. So I will keep only this portion, only electrons. So my operator will be identical to dipole operator for 2 electron system, and I can call mu. So it will be summation of position of electron 1 and position of electron 2. And probably I will skip doing vectors and do it only one dimensional, otherwise it will be too much of writing. Okay? So I'm going to place this mu in the center of my sandwich between bra and cat. The actual bra and cat procedure will correspond to performing integration over R1 and R2. And my bra on one side will be this product of wave functions, bra, and this will be cat. So in bra and cat, for bra I probably should put star. So in bra and cat, first electron resides on the first orbital and doesn't change. But the second electron jumps from orbital 2 to orbital 3. So there is a difference between bra and cat before and after excitation. So here is the little exercise that I'm going to practice. Maybe at this point you already developed some level of irritation against the instructor for the specific purpose. It may not be clear why we need to torture our brains with this exercise. There was a general introduction that we will discuss interaction of light and matter, but it will be completely normal if by this point someone feels lost in transition. So please give me a little sign if maybe if a little reminder is needed, what is our expected goal, or when we will finish this torturing mathematical exercise. I see only smiles. So shall we, if you're okay as we go, or minus if we if I need to give a little. Okay, thank you, Sarah. So as you remember from 2 months that we are studying this subject, that multi-electronic wave functions are a big challenge, and we achieved a great success of reducing multi-electronic wave functions into one electron mean field theory, which is hardly possible. But now when we speak about observables, about a bridge to real world, we still see this multi-electron wave functions, multi-electron operators, which we may hate because they're so complicated. So my main goal is to prove that one can practice one electron picture, even if telling by optical excitation of multi-electron system. So as a result of this consideration, in like less than 5 minutes, I will show that probability of transition can be expressed in terms of one electronic orbitals. So something will be much simplified in this expression. So it will be recast in terms of one electronic orbitals. So one can describe optical transitions in terms of one electronic orbitals with reasonable precision, reasonable qualitative accuracy. Whew. So, yeah, I think if one practices this expression, there is product, then summation, and then product again. If I open brackets, there will be 2 terms, and in each term there will be a product of 4 wave functions, right? In the first term, there will be phi1 r1, phi2 r2, then it will be r1, then will be phi1 r1, phi3 r2. And in the second term, it will be the same things, but in the middle will be r2. So let me show. Yeah, there is a ugly writing by hand, but I think this computer typing is better. So we open brackets, and we have phi1, phi2, phi1, phi3, and in the middle is r1. And the second term does have r2. And each term includes integration over r1 and r2. So why, and maybe it is the longest expression, the longest equation. Later on it will roll down here. Why do I need this relatively long mathematical expression? I want to practice orthogonality. We agree that atomic orbitals may be non-orthogonal, but molecular orbitals are orthogonal, right? So I'm going to use the property that phi1, phi1 is 1, but phi1, phi2 is 0. So, and anything else, when indices coincide, it will be 1, indices do not coincide, will be 0. So please help me to identify if there are any orthogonalities in the blue box. I didn't ask Lola about anything. Yes. Oh, would you like to help me with the blue box? So let me explain what I'm looking for and how to help me. I'm looking for a term that does not will not have r1, will have only wave function. I need to such term that includes integration over variable r2 and functions that depend only on r2. So would you guide me? What should I highlight? Like which function depends on r2?
Phi2 star and phi3.
Thank you. And this phi without star r2, right? This one.
Yes, I phi 3 because this is
Okay.
3.
Thank you. Thank you.
Oh, it shall be phi 2. Oh, okay.
Thank you, Laura. So I can take the yellow part out of bracket because integration over R2 and integration over R1 are independent. Those are independent variables, right? So out of the blue box, I can take this little yellow thing and it will read the following way: integral dr2 phi 2 star r2 times phi 3 without star r2. So, or in the Dirac notations, it will be phi 2 times convoluted with phi 3. What will be the answer of this?
0.
Zero. Yes. Yes, correct. Thank you. So, and if one factor in the expression equals 0, then the whole box is equal 0, right?
Yeah.
So, what an easy life. It is twice as easier. Thank you all. You did help us to get through. Now,
No, it's me, Kia.
Kia, okay, Kia, please. Now you see in the second, in the red box, we do have R2 in the middle. And please.
It should be 1.
Yes, but please help me to highlight for everyone. Please help me to find those terms that will depend on R1.
Phi 1 star R1.
Okay.
And then there is phi 3.
No. Depending on R1.
Okay. Depending phi 1 R1. And then it's equal to 1 because of orthogonality.
Exactly. Thank you. So we are extracting this blue factor out of the blue box, and if you pardon me being short, it will be just phi 1 equals 1. Okay. Yeah. Thank you, Kia. Now it means that I can completely cross through everything, this blue stuff, and we have substantially smaller number of terms. So we will have only amount of colors. I didn't try. Okay. So I have only integration over R2, this wave function, this R2 in the middle, and this phi 3. Okay?
Yes.
And here is, I would say, the magic. So we started from finding matrix element of multi-electron wave function, but now we are coming just to a product of two one-electronic orbitals with position operator in the middle. And this trick can be done even if you have like 10, 20, 100,000 electrons. Only the electron that is traveling from one orbital to another one contributes to this probability of transition. The rest of electrons predominantly will give no contributions. And it is really wonderful result. So here one can call it matrix element between ground and excited, and basically we have better writing of it. Yes, so matrix element of position operator between orbital 2 and orbital 3. But most important that it is one electron matrix element. So I will switch the gears to a slightly different subject, but please consider to memorize it. We will come back to this derivation again and again through the course. It is something that we will need for course and for the project. Okay, Now a little bit on the periodic models. So suppose we have a model that consists only of two atoms, but they are repeated again and again. So this little box is repeated, right? It is a repeating unit of a polymer. And I draw two atoms because I'm lazy. Typical models have a little bit bigger. So one can find the position of the same atom, like atom number one, in first cell and second cell, and subtract the vectors between them. So distance between the same atom in different replicas is called translation vector, right? And if you have the third replica, so the position of each atom in the next unit cell will be same as it was in the first cell plus translation vector. If you have the second cell, then it will be position in the first cell plus two translation vectors, right? And if it is not one-dimensional polymer, but two-dimensional, three-dimensional structure, then there will be translation vectors in each three directions, like A, B, and C. The general definition of the periodic structure is that potential nuclear to electron interaction in the shifted position and in the original unit cell are the same. So if you add the vector which is multiple of translation vector, the potential will stay the same. In a rigorous way, it is a definition of periodic model. Now the question, and in the following slide I will overview rather than derive. The question how the periodicity of the model will reflect on properties of electrons, of electronic orbitals and electronic energies. So electronic, or like if you have positions of ions, then near each ion in the first cell, in the second cell, in the third cell, the potential, which is described here by red line, will be repeatedly the same. But the question is the blue line here, highlighted with different color, blue line, which is electronic wave function. Will it be the same or different when we look on the next atom in the periodic cell, in the next cell? And there is a theorem after this Felix Bloch that wave function will be the same by absolute value, but it will gain additional phase factor. It will be multiplied by a complex number, and this complex number will be repeat as we go through large number of the cells. So this thing in the box shows how the wave function or orbital will change if you move from one unit cell to its replica. So the part that is not getting changed often referred with this letter U and called atomic part, and the stuff that is getting accumulated as we go from cell to cell is related to plane wave electronic function. So it is a standard way to seek for orbitals or electronic functions in periodic solids. Okay. Now I'm speeding up and I'm almost done. Now I will take the least time for most pleasant part. So do you remember this equation? You can show yes or no. Or please give signal, raise hand, or tell if someone doesn't remember this equation. So Boston supports. Lina? No? Okay. then
I remember the concept and idea, but the equation, I forgot it.
But can you briefly tell what this equation is about? Or you can just read the title in front of you.
So, as we dealt with single electron wave function for Hartree-Fock, it was summation over the electrons, but for total energy.
Okay.
So what actually?
So those are not orbitals, but orbitals energy, right?
Yeah.
And what is this J and K? I may swap the same, but so Sarah, would you like to help us? What are those pairwise contributions with two indices?
I'm not sure. Maybe they're referring to electron.
Yes, but if one electron is referred by one index, then which objects are referred by two indices? Just two electrons, right? And which energy corresponds to two electrons? Let's scroll through to the beginning of the lecture when we go over. Yeah, it was. Remember, we computed them through atomic functions, and I remember we were drawing Feynman diagrams for electron coming in and out, and having wave line between them. One diagram, and another was for electron was bypassing each other. What are the keywords for this J and K? The one who wrote in the chat line is correct. So let's try to remember this once. So how electrons interact with each other? Which law from classical physics?
Coulomb.
Correct.
And exchange.
Correct. So the one that goes here is Coulomb. The one where the swap is exchange. Okay. So Hartree-Fock energy is contributed by both single electron orbital energy and pairwise Coulomb exchange between pairs of all occupied orbitals. So we go from one to home, right?
So,
now,
Professor,
yes.
Professor, one question. So, for Hartree-Fock, as I remember that it's the summation of like kinetic energy and potential energy of nuclei. Then after that, this Coulomb and exchange this one. So, but there, okay. So, orbital energy, it's included kinetic energy and potential energy both. Okay. Maybe.
Okay. Okay, I got your question, and if you give me a few minutes, I'll answer a question and complete the lecture. Both it is at no time. We do not have much left. So to the question of care, which we construct Fock operator, which includes this 4 energy. which indeed has kinetic gradient plus interaction with nucleus. Yes, but we want to formulate everything in a matrix form. Therefore, both core part and this Coulomb exchange are formulated in terms of matrix elements between orbitals phi I and phi j, or here I think we call it mu and nu, but in terms of matrix elements. And if we already know matrix elements, then the energy will be just summation of this matrix element between all pairs of orbitals. So original Hamiltonian, yes, it is expressed in the differential form. But now we have already converted our consideration from differential form to matrix form.
Okay.
And all considerations are now in goes as matrix elements. And now if we found orbitals and their eigenstates and matrix elements of the Coulomb exchange in terms of the molecular orbitals, then we can find total energy for all occupied orbitals. It will be energies of everything we occupied plus Coulomb exchange. No. Oh, I think I was answering it to someone else in the previous year.
Same question.
Now, we are going to make very big approximation, which is, some people may not forgive us this approximation, but it is needed for the sake of quick calculation. What if we just for a short time assume that Coulomb and exchange are approximately equal and do not change total energy much? This is very wrong. In practical situations, is a very big approximation. But for easy life, let's assume that temporarily we forget about them. Then total energy of a system that connects so many electrons, we need to add together energies of all occupied orbitals, right? Okay. And now we are going to discuss affinity, electron ionization and affinity. So about 3 years ago, there was a student, Christian News, who was delivering this ionization and affinity during his presentation for Gaussian, and I borrowed his slide. So here are orbitals, including HOMO and LUMA, and the ionization if one removes electron from HOMO, affinity if one places energy on LUMA. Right? And in fact, if one thinks from experimental point of view, ionization means that one looks for total energy of a system where number of electrons is reduced by 1. Or we physically removed electron, we ionized the molecule, right? Now, in the I'm showing 3 tables and with ugly writing captions. Yeah, here is better. So in the central, it is neutral and with total charge 0. We have occupied orbitals, and at each orbital we have 2 electrons, right? Then we have virtual, and we have no electrons. Now, if we remove 1 electron, the easiest way to remove it, take it from HOMO, right? So if we change number of electrons by 1, if we actually remove electron. By the way, chemically one can call it cation, charge +1, and in Gaussian calculation we will need to put charge 1 instead of 0. So here on the former HOMO, we will have 1 electron instead of 2. And if we compute total energy of the system with number of electrons by 1 less and subtract the total energy of the system with original number of electrons, this will be exact ionization energy, right? Now let's look on the affinity. If we, sorry. Yeah, if we contribute an additional element, it will be contributed to LUMO, right? So in HOMO there are 2 electrons, in LUMO there is 1 instead of 0. And if the charge will be -1, in chemical language it will be anion, right? And the system, the molecule will have n+1 electrons. So we will need to look for subtraction between this total energy and this total energy for exact electron affinity. Now a little hocus pocus. So if we take approximation of Koopman, if we neglect Coulomb exchange, if total energy of system equals just to summation of all occupied orbitals, then for neutral, and I'm about to finish. If we are looking for total energy of a neutral molecule, we'll have energy of first orbital plus energy of second orbital. And in fact, we need to multiply by 2 if there are 2 electrons per orbital. But so going so forth, energy of orbital n-1, and then energy of the last orbital, where n is number of electrons. Make sense? Everyone is okay? Okay. Now, if I remove 1 electron, then total number of electrons will be -1, and total energy will be E1, E2, En-1, and then in place of E sub n will be 0. Correct? So if we subtract these 2 numbers, the difference will be equal to the energy of the orbital number n. So it will be electronic ionization approximately equals to energy of the HOMO orbital, right? So it is literally derived if we neglect Coulomb exchange. And the same trick for addition of an electron, for anion. So if we populate the LUMO, there will be contribution from orbital n+1, and we will have E1, E2, En-1, E sub n, and then E sub n+1. And if we subtract these 2, we will get energy n+1, which will be energy of LUMO orbital, which is I should go first. Ionization energy. Ionization energy, and here electron affinity. Make sense?